Hello, everyone. Thanks for coming. My name is Denis. Today, we were going to talk about full text search, tips and tricks. For those who don't know me, I'm a developer advocate at Couchbase. I'm a Believe enthusiast, and I have been developer for quite a long time. I had an SEO startup in the past. That's where most of my knowledge about search comes from. And I also have been using Solr quite heavily for a long time. So you might be asking why someone from a database company is talking about full text search. So Couchbase is famous for being highly scalable or have a good performance at scale. So a normal database will have around 5 to 6 nodes, and Couchbase you can scale to hundreds of nodes in the same cluster and still be highly consistent. And in this scenario, it's kind of hard when clients want to do full text search to push data to Elasticsearch or Solr, for instance. So a while ago, Lucene, both Elasticsearch is Lucene is Java, and we still have a lot of those problems with JVM with Java. So a while ago, we decided to create a new framework called Believe. It's 100% open source, and it's written in Go. And I'm more than invite you to contribute. We are the major contributors for this, but we have been receiving a lot of pull requests around the world. And that's basically what we have here inside Couchbase. So this is the Couchbase web console, and when you go to search here, under the hood, we are using Believe. So, but today I would like to talk a little bit about search in general. The agenda is pretty much coding, so live coding. If you believe in the demo gods, now is a nice time to pray for them to be kind today. So search is pretty much one thing that developers think about search is matching. And search is not about matching. Matching is a very simple problem. We solved matching text a while ago. Search is usually about, is more sales oriented, right? So whenever the user search for something in your application, you are trying to convert the user to do something. So if you think about Netflix, for instance, they are trying to convince you to watch a movie or series. Google is trying to convince you to answer your question and show relevant ads. And Amazon is trying to show relevant products for you to buy. It's important when you are designing a searching feature to understand how users search. So one common mistake that I see is developers don't store the queries that users make. So you don't know, okay, how your users search. They have no idea because you are not storing the queries. And okay, once you show something to them, which result they chose, and yeah, they are also not storing that. So you have to, when you are building a search mechanism, you have to store all this data, like what they're asking for and which results they are choosing. And this is just an example it's already like 4 years old, but this is one of the best data I could find of how users search on Google. So you see that 25% of the users use just one word, and 50% use from 2 to 4 words. And that's pretty much the range you have to return a meaningful result to them. Okay, some quick concepts here. Probably you guys already used to TF-IDF. So TF-IDF basically says that higher words rank higher or score higher. Edit distance is how much costs for me to transform one word to another. So, for instance, star to convert star to start, it just takes me one operation. I only need to add one word, right? It's also called Levenshtein distance. So probably you guys have heard about this. And we also have pivotal length normalization. So if I match a text in a small text, it will have more relevance than matching the same word in a bigger text, right? It's pretty straightforward. Oops, no, we didn't finish yet. Yeah, we are far from finished. Okay, let's start then. So first, I have a very simple search here. My application is not running yet. So here's basically I received the word here, and I use believe internally to basically search this query in my database. I have a very simple index here. So basically, I just say, hey, index all the fields of this kind of entity here. And I have an application called Couchflix. I know this is much better than Netflix, right? I'm kind of proud of the name. They missed an opportunity. So if I come here and say Star Wars, okay, we have some moves here, right? Not the best result ever. Let's try Star Trek. Okay, yeah, we have some Star Trek moves, but Trek is a very hard word, right? So probably even if I search Trek, I will still get some good results about Star Trek here. What if instead of Star Wars, I get Star War, for instance? Well, not even one result about Star Wars. So we have, this is basically something like users just think that, hey, I just throw data on last search and we get good results. That's not how it works. So let's try then to improve our search here. So I'll come here and create the version 2 of our search. Now we are calling here version 2. And instead of making this query, I will create a disjunction query here. A disjunction query is pretty much like a OR. So I would try to try this or this. So I would try to match the title. And I will get disjunction. And here I have word I'm receiving and title. Title is the field that I'm trying to match. And now I'm using title here. I will stop my application, start again, and duplicate this tab. So just to show you guys what I'm doing here, disjunction, I'm matching the exact word, and also I'm matching the same phrase, but with a leverage time distance of 1. So if someone search for star or start, I will match both use cases. But of course, as star is an exact match, it will rank higher. So we can come back here to our search 2, probably at this point. My application is already running. So let's try again Star War. Not good enough yet. Okay, let's try to add more fields to our application. So let's come back to, let's stop our app, come back here and add the version 3. So here, version 3. Let's add now some other fields. Let's call this overview. Overview. And we also have original title. And now, as this is or, so I will join them in a big OR, right? That's how it works. So FTS, search, query, disjunctions, and then I have title, overview, and original title. Okay. And now I put this on FTS. So, just to give you an idea of how my database looks like, let's pick a movie here. So this is all the data I have about the movie. So we have collection, budget, original language, overview, production company, cast, what else, genre, crew. So I have basically everything. This is an exported database from IMDb. My application is running. Okay, let's duplicate the tab and search for Star Wars again. Not good. So this is where developers usually got confused. So what's happening here? So one of the problems is star and wars and war are being matched separately. So if a movie have war, war, war in the text, and another movie has only star war once, the war, war, war will hang higher. So we have to treat how we index your data. So one of the strategies to do that is to use shingles, something called shingles. So basically, a shingle will break your terms in combination of 2 or 3 or 4. That depends. That's on you. So if I have a query like Star Wars Daisy Relay, I will break these terms in Star Wars, Wars Daisy, and Daisy Relay. Of course, I have some noise here, but it's still fine. I have the Star Wars and Daisy Relay. This is how I'm matching the. This is those matches will be very good. So I already have the index here ready because it takes a while to create. But basically, I have all the fields here, all the matches here. And if you come, let's say, title, I'm using title analyzer, and title analyzer here is using to lower. So I transform to lower. I remove stop words, and I'm indexing with a Shingle simple. So Shingle simple will basically, when I come here, I will come and say Shingle minimum is 2 and max is 2, so we'll break in 2 words. And I'm adding the original tokens here, so even if I match a single word, I will still return some results. This is not exclusive for Believe. Everything you see here, you can apply on Solr or Elasticsearch. This is pure a theory about full text search in general. So let's come back to our application here and then create literally the same application, but now 4. And rename our index now to movies Shingle, right? And now we will call this here. This is the name of movies Shingle, yeah. So search for, yeah, I renamed the wrong one. Search for. And here, search for, yes. Movies Shingle, yeah. There is a lot of stuff you should literally play and understand how indexing works. Because, for instance, we could, instead of shingles, we could use steaming, for instance, like to avoid conjugations. So fishing, fisher, fished will become fish. So you can kind of deal with a lot of those language conjugations. So you can kind of remove some of the noise of your search. Hopefully, it's already running. So let's duplicate here and start war. Voila! That was one of the biggest problems. Now we can start thinking about boosting, right? This is probably most of people, when you don't have a very good result, they think about boosting, but you have to think about how do I index data first. But now it's kind of the time to think about boosting. So first, when you think about boosting, you have to think about ranking factors. So for Google, for instance, title is very important. The URL is very important. How many backlinks you have. So for your application, and of course, there is a lot of types of ranking factors. So you can use the standard ones like data about your data, signal. So if the user always click in the same results, you can rank this result higher. Personalization. So if I like science fiction movies, you can always boost those movies for me. And this is an example of how Google distribute the rank factors for local search. This is basically some of studies, of course not published by Google itself, but people who are trying to understand how Google works. And of course, when you start planning your factors, your rank factors, it's pretty much a guess, right? You start, you guess your rank factors, and at some point you say, hey, yes, now it feels good to me. So here we can in our application, let's create now version 5. Version 5. Here, version 5. Okay. So we can put like boost for 40%. Our title, overview, too much text doesn't work to boost. Original title, maybe 10%. Okay, what else can we boost? Well, we all like recent movies, right? I personally don't like movies from the 70s or 50s or something. So we can also boost using the year, the release date, or release year. But there is some problem with the release date. Well, okay, if a movie is from 2019, yeah, that's awesome. But if it's 2017, okay. But I really don't care if the movie is from the 2000 or 2004. It's already a long time ago. So you can just simply have a linear boosting for those kind of fields. And this is, for some fields, you have to think about decay functions. So yeah, it's important for me that I will boost higher movies that are 1, 2, 3 years old. And then I will drop according to some function over time. This is pretty much, for instance, how Hacker News work, right? So in Hacker News, you have even though you have news that have 1,000, 2,000 votes, in just a few days, it's out of the first page. But then over time, it's not penalized anymore. Look, it just stays there in the same position. And that's pretty much how decay function, because it's not linear. In Believe, we haven't implemented this yet, but we can use range boostings. So I can show you guys here. So I can now create a conjunction query here. Conjunction is pretty much like an AND. So conjunction query, and then search query, conjunction. And now I will join this FTS search that I'm doing here with my boosting release year query. Okay. Now I can already, oops, nope, this is not gonna work. And now I'm using the conjunction query here. So, of course, I can boost for other fields. I can boost for runtime. I can boost for popularity. I can also boost by ratings, right? But ratings is also something very complex, right? Because a 3-star movies for me might be a 5-star movie for you. So how do you normalize that? So there is some strategies to normalize user ratings according to how they rate. But we are not doing this here because of the short time. Another thing that I would like to come up with is, how do I evaluate ratings? So I have one movie that has 20 votes and 5 stars, and another that have 3,500 votes and 3.8 stars. So you can use math for that. So you can come up with some confidence, how much confident I'm about those values. And that's pretty much what we can do here. So if robot chicken, application array running here. So let's duplicate here again. Duplicate and start war. And yeah, we still have some results here. I don't care about robot chicken, and I would like to bring maybe Star Wars and Rogue One as one of the first results, right? So let's compare those. So Robot Chicken, for instance, has here, Rosa has 68 votes, and the average rating is 6.9, and we have a confidence of 1.7. And Rogue One, for instance, have more than 5,000 votes, 7.5.4 average rating, and a confidence of 685. So instead of using ratings directly, I can calculate this and use this as to boost my algorithm. This is, of course, is already made because you won't do this during the query time, because in the query you have to be as fast as possible. So let me just turn my notes here. And yeah, and of course you always need to also plan your business rules, because sometimes you are doing the most relevant search ever, but your manager will say, hey, I don't care, just boost those fields here, and I want those products to be to rank higher. So let's implement all the stuff here in the code at once, because I'm trying to save time. Now we can create search, maybe 7, 8. This time we will boost here popularity. If the movie is promoted, or it's just a false or true value that I have, I will also promote this, boost this movie. Runtime is also here, and ratings. Ratings. Okay, so this is our version 8. Right, so of course, in a real application, you will never change more than one thing per version, because now you don't know, okay, what's really changed in my code, but we are doing this, trying to save time. Okay, let's run again our application. This should bring us much better results. Oh, sorry. Yeah, thanks. In the meantime, let's duplicate this again so we can compare. This example is already on GitHub, so you guys can play with it. One cool thing about it is you can view exactly why this is ranked higher than this one. So here, for instance, you have all the matches here and the score. So you can compare, let's say, why this is ranking higher than this here. So you can see the matches and the score. Now our application is already running, so let's try to run again the same query, but now with promoted, boosting popularity, boosting release year, boosting ratings. Star Wars. Very good. We are doing great now. So now we have Star Wars, Force Awakens, and Rogue One as the first result. We have the classic Star Wars as third, and Robot Chicken here, for some reason, is still very relevant. Anyway, next thing. So let's add facets for a search. So if you don't know what facet is, pretty much when I searched for notebook on Amazon, facet is this thing here. I can facets. I can kind of filter which kind of search results I want here. So to do this, let's create a new version of our application here. So search 9. This time we will add facets here. And now search 9. So yeah, Now I receive a map, string, list, string, facets. Okay, and after the conjunction here, I say if facets is not empty, my conjunction query, my end here, I will add filters. Basically, I'm just add end, so I will say, hey, if you send genres equals to comedy, I'm filtering to just get comedy movies here. And that's my conjunction query and my facets. And here on my query, I have to specify which facets I want. So I can do add facet. I will call just this facet genres and search search facet, here, term, and then I use genres dot name, and I want you to return 10 genres for me. Okay. Let's restart our application. This genres here, genres.name, is coming from my index. So in my index here, I'm indexing genres, which is a list, and inside genres I have names. So that's where it comes from. So not yet, but we can, in the meantime, duplicate here. And yeah, let's try it out. Star War. Not yet, not yet, not yet. Yeah. And now we have filters here. And if I come here and say comedy, well, I have Robot Chicken. If I say documentary, I have here Star Wars documentary. So this is one of the cool things you can do. Let's now, one of the things you should also think when you are building search is what the user is trying to do, right? So one common thing that we do is also search for the actor's name. So let's search for the actor name here. So let's implement search 10, version 10 here. Call here 10. And here, is this the version? Yeah, 10. No, 10. We can also add on the disjunction, so because it's on OR, I can also add here get actors disjunction. I will explain this later, but and here I have to pass words. Okay. So actor disjunction is basically pretty much I'm trying to match the user, the name of the cast or the character. So I can, like, if I search, I can search for Buzz Lightyear or for Eddie Murphy, for instance, and I will match in both cases. Let's come back here and duplicate again, so we can compare with this. Yeah, let's try now Eddie Murphy. Okay, we got two Eddie Murphy movies, but well, Eddie Murphy's did much more movies than that, so something is wrong here. Let's try another actor, so maybe Bruce Willis. No Bruce Willis movie so far. So what's wrong here? Well, usually most of the searches, they have a bias. So our search so far is heavily biased on the title or the topic in general of the movie. So when we want to search for something else, here the user is trying to do another type of action, right? He's trying to search for an actor. And so far, we implement something to search for users, for movies, movie titles. So one of the most classical things in full-text search is to identify what the user is trying to do. In this case, what can we do here is to recognize some of the entities that we have in the search term, and then change the boosting factors that we have. You don't have to implement this by yourself. For instance, Solar has the Solar Tagger extension, or you can always use some cognitive service. So, for instance, Azure has, you can give a text to Azure or Watson, for instance, and they can let you know, hey, I found those entities inside this text that you gave me. Of course, you have to do this not on the search time, because in search it's supposed to be fast. And here, this is pretty much what I did, but I did this with, as I already had the data set with all the actors, and Couchbase has a key value store internally, so I converted the actor's name to a key, and then I simply try to match it and see if I have the actor name in the database, and if I have, I remove this this name from the term, and I change the ranking factors to boost my queries, my result according to the actor's name, not the title of the movie. So here, instead of implementing something from the scratch, I can call search 11. Search 11 is already here. So here on search 11, what I'm doing is same thing, but then on actors disjunction here, well, first, I have this movie query parser, so it will parse the terms. And in the terms here, I basically remove, if you used comedy, crime, drama, science fiction, all those words, I remove them. I say, hey, the user is trying to search for a category, so drama, comedy, or whatever. And then I try to extract actor's name. So I pretty much create a shingle. So because you never, if you just search for Bruce, doesn't make a lot of sense, right? Or if you search for Will Smith, you always use Will Smith, not just Will or Smith, because those are two generic words. So I create shingles, and I try to match those shingles against my database of actors. And if I find something, I remove this actors from the term, and then I return here all the entities that I found. And if I have found any actor, I basically change my boost fields here. So I boost for 50% if I have found an actor in the search term. So now if we come here and let's duplicate this instead and search for Bruce Willis, yeah, we have Bruce Willis movies now. Nice. If you try to add Murphy now, add Murphy. Same thing, just add Murphy movies here. Let's try Bruce Willis again, just to compare. So one of the problems with this search now is those are not the best moves that Bruce Willis made. So probably there's something going on here, right? So we are boosting by rating, we are boosting by release year, we are supposed to get better results than this. So TF-IDFs have some pitfalls. So one of the things is sometimes you don't care about the size of the text. You only care about, hey, is this the text there or not? In this case here, for instance, this movie here, I'm matching in the cast, I only have 4 items. And in this, if we come back here and let's say get this movie here, I have 8. So this is pretty much TF-IDF screwing up with you. So what we can do is adjust the actors array to have nearly the same size, for instance, so you can mock up data or remove data from it. So because anyway, most of the main actors are the first 3, 4, 5 names in the cast. Of course, if we are talking about like Avengers, then this won't work. But well, this should work for us. So we can create here search 12. Here, let's go down here on search 11 and copy our whole method here and create search 12. And now, instead of using get actors disjunction, I'll get the adjusted one. So the adjusted one basically use cast adjusted, which is another field that I have that array adjusted the number of the size of the array. And we can come back here and run again our application. Sure. Yeah. Now we can duplicate and compare. Running, yep. Let's search for Bruce Willis. Let's wait. Nope. Come on. Yeah, here it goes. So maybe not the best movie so far, but this is certainly more relevant than the ones we got. So just to compare a little bit here with other searches, let's go to our competitor here and try to search for Bruce Willis. So yeah, we are getting Bruce Willis movies here. Let's come here to this one. No, no, no. I don't want to watch it. Here we have category comedies, right? So if we search for comedies, yeah, it works. If we search for Bruce Willis comedies, no results. Let's come to our search and search for Bruce Willis comedy. Yeah, it works. So, well, in 40 minutes, we implemented a very decent search. And not using any machine learning or anything else. It's just understanding what's relevant. Of course, when you are implementing a real application, you will not test like I'm doing here. This is more for a show, but you have to, first, you have to use this current field evaluation method. So every single change you do in your model, you have to compare and have a list of, okay, this is the query, this is the best results that I could have from this, how far my model is from the ideal result, right? Even Google, they do the same thing. Like they hire normal people to come to the office and evaluate what search is better for you. So is this or is this? They literally have, you can find on the internet, like they have this 2 screens and you can see, okay, this search for me on Google is better than this one. They do the same thing. And this is one of the things you have to do. So it's not simply JUnit test that we are used to do. So it's a little bit more complicated than that. You have to use precision and recall. So how far you are from the ideal result and how many results you brought. And if you really like this type of methodology, there is a really nice course on Coursera called Text and Retrieval and searching engines. I do recommend you guys to do the entire specialization because it's really good for understanding how text works in general. Let's go back to my slides. One thing that you should also pay attention is black hatting. 15 years ago, 10 years ago, to be honest, it was quite easy to trick Google, for instance. All you have to do is to, if I want to rank for Bruce Willis, I would just write like Bruce Willis 100 times in my page, and that's it. And I could just hide this from the user using display none, and Google will be triggered by that. Of course, now they are much smarter than that. So if you are planning to search, and if the users can gain something when they rank higher on your system, you should be aware of, hey, how do I handle black hat? Of course, this is also topic for another talk, but this is one thing that you should pay attention, and that's why whenever you, for instance, on Amazon, when you announce a product, they review it first, just to be sure that, hey, yeah, you're not doing any kind of black hat. Some further reading, of course, I do recommend you guys to check it out, Blave Search, and contribute if you like. There is a very nice book about called Relevant Search with applications for Solr and Elasticsearch. Dumbing Text is also a quite famous book about it. Solr reaction is a kind of a common recommendation. And of course, if you can, if you're interested, check out couchbase.com. We have a lot of material there. Couchbase, we have Couchbase community that you can use, and is nearly 100% open sourced. This is pretty much what I have. I hope you guys enjoyed, and thank you very much. Questions now? By the way, if you go to GitHub and you search for Couchflix, you will find this demo there. And of course, the one thing, if you want to play with this, it took me 2 weeks just to parse the whole data and put in a decent format. So if you want to play with this movie data set, probably you can find this here. Okay. Thank you very much, guys, and enjoy the conference.